Welcome to This Explainer. We hear a ton about solar panels, wind turbines, and massive battery parks these days, but behind the scenes, grid operators are actually facing a massive stability crisis. Today, we're diving into the heavy metal solution that's quietly holding our electrical world together. We're looking at how a classic piece of technology, the synchronous condenser, is experiencing a huge renaissance to save our modern, renewable-powered grids.
Let's kick things off with a fundamental question. As we transition to renewable energy, what actually happens to the stability of our power grid when the spinning stops? It's a huge deal. The rapid decommissioning of centralized heavy rotating mass leaves a systemic void in our infrastructure. For decades, those massive synchronized turbines acted as an invisible physical anchor for the whole network. Without them, we're looking at a structural deficit that genuinely threatens baseline stability.
When you compare the two, it's pretty stark. We are rapidly shifting away from a highly centralized grid, one that was anchored by all that physical spinning mass, to a distributed web dominated by wind, solar, and power electronics. This future grid is an incredibly complex network relying heavily on inverter-based technology. But here's the catch. That shift leaves almost zero physical inertia in the system. And that brings us to the hidden flaw of this whole transition. While our new grid is absolutely cleaner, it's also structurally weaker. Because it lacks the heavy rotating mass that traditionally gave us physical strength and high short-circuit ratios, the entire system becomes hypersensitive to disruptions. So, it's a massive upgrade in sustainability, for sure, but a significant downgrade in physical resilience.
To unpack how we bridge this gap, we're going to break this down into 4 parts. First, the changing power grid. Second, meeting the synchronous condenser. Third, providing critical grid stability. And fourth, real-world synchronous solutions.
All right, part 1, the changing power grid and exposing its hidden fragility.
So, relying purely on inverter-based resources brings some serious vulnerabilities to the table. Imagine a sudden disturbance hitting the grid, like a huge cloud bank suddenly covering a massive solar array. The system immediately experiences what's called a dangerously high rate of change of frequency, or ROCOF. Couple that with phase-lock loop instability and fundamentally low short-circuit levels, and operators are suddenly fighting deep, unmitigated voltage dips. If left unchecked, those dips can cascade and literally trip major industrial infrastructure right off the line. Which leads us nicely into part 2, meet the synchronous condenser, an old hero reborn. So what exactly is this thing? Well, a synchronous condenser is effectively a massive, free-spinning machine. Think of it like a giant physical shock absorber for the power grid. But here's the wild part. It doesn't actually generate any active power. Instead, it spins perfectly synced with the grid's alternating current, acting as a massive sink and source of reactive power, or MVAR. It gives us the exact physical stabilization of a traditional turbine, but it's deployed purely for network resilience.
Now, you can't just flip a switch to start a massive rotor from a standstill. That would cause absolute chaos on the grid. It requires a precise sequence. First, a dedicated, smaller pony motor smoothly spins the condenser up until its frequency perfectly matches the grid. Second, the excitation connects and the voltage regulator kicks in. Third, the breaker closes, bringing it fully online. And finally, that pony motor just de-energizes and idles. From there, the momentum of the grid itself takes over, keeping this colossal rotor spinning and ready to absorb any shocks.
Moving on to part 3, providing critical grid stability. Let's look at the 3 pillars of how this actually works.
The first pillar is inertia. The condenser acts literally like a giant kinetic shock absorber. Its massive physical momentum instantly fights back against any sudden shifts in power supply or demand. If generation suddenly drops, that huge spinning rotor physically resists the deceleration of the grid's frequency. It literally buys the network crucial milliseconds to balance the load, completely mitigating those scary high ROCOF events we talked about earlier. Pillar number 2 is fault-level contribution. Here's the issue. Inverter-based renewables tightly control their output, which essentially blinds standard grid protection systems during a short circuit. The Syncon fixes this instantly. When a fault occurs, it injects a massive, uncontrolled inductive fault current. That huge spike of current is exactly what protective grid relays need to detect the issue and clear the breakers safely and immediately. And the third pillar? dynamic voltage regulation. By rapidly adjusting its internal magnetic excitation, this machine can seamlessly switch between overexcited and underexcited operation to either produce or absorb reactive power. It basically maintains precise grid voltage limits in real time, acting like an instantaneous physical voltage regulator for the whole network. This breakdown elegantly ties it all together, mapping the grid's challenges directly to the condenser's solutions. Whether you're dealing with the steep ramps of the duck curve or deep voltage dips from low short-circuit levels, decentralized Synchronos provide the exact physical corrections the grid needs. When you strategically place these machines at vulnerable nodes, they literally transform a fragile, transmission-constrained network back into a robust, strong grid.
Let's bring this into the real world with Part 4. Real-world synchronous solutions powering the future today.
This isn't just theoretical engineering either. Companies like ABB are already building entire plug-and-play synchronous condenser packages. Here you can see a complete setup featuring the condenser itself, the cooling units, and the auxiliary controls, all neatly integrated into a single cohesive footprint. This means network operators can efficiently deploy these installations exactly where their transmission infrastructure is the weakest.
And the scale of what they can do is just amazing. By coupling a mid-size 70 megavolt ampere condenser with a dedicated spinning flywheel on the exact same shaft, engineers can achieve a massive 450 megawatt seconds of stored kinetic energy. That flywheel vastly multiplies the physical inertia, creating a deep reserve of energy that makes the local grid incredibly resistant to sudden shocks. What makes this modular approach so brilliant is the sheer efficiency. To put it into perspective, a gigantic 300 MVA single unit needs about 4,800 kilowatts of electrical energy just to keep itself spinning. But this modular 70 MVA unit, combined with that flywheel, delivers the exact same stabilizing inertia while suffering only about 1,300 kilowatts in electrical losses. That's over 3.5 times fewer losses. It's a total masterclass in grid efficiency.
And we are already seeing this exact technology deployed out in the wild. Check out this site, actively supporting a massive energy park in Queensland, Australia. Running right alongside a mix of solar, wind, and battery storage, these package condensers are working proactively to ensure that all that localized green power generation doesn't accidentally destabilize the broader national transmission network.
The tech is even evolving into some incredibly advanced hybrid systems. Take a look at this installation commissioned in November 2019 at Neilston in the UK. It perfectly marries the ultra-fast, super precise solid-state electronics of a STATCOM with the heavy rotating mass of a synchronous condenser. By sharing a 3-winding transformer, operators get the absolute best of both worlds: lightning-fast dynamic MVAR control and unstoppable physical inertia.
So, I'll leave you with this final thought for today's explainer. As we race to build the distributed, renewable energy network of tomorrow, does the true key to our grid's future rely not just on generating new energy, but on mastering the heavy, spinning technology of our past? The synchronous condenser proves that maintaining a reliable network in the clean energy era still absolutely requires massive physical engineering. Thanks so much for joining me, and I'll catch you in the next explainer.